Section 2.6 is on limits at infinity and horizontal asymptotes. These two things are very closely related. Note that limits at infinity does not mean the same as an infinite limit. These are two different things. When we say limits at infinity, we mean to say x is getting larger and larger, okay? Whereas when we say an infinite limit, we're saying that f of x is getting larger and larger. So it's two different things. Let's explore this a little bit deeper. So this is the first thing that I mentioned, right? X is going to become arbitrarily large, either very negative, like a million, a billion, a trillion, or either very positive, a million, a billion, a trillion, or very negative, minus a million, minus a billion, minus a trillion, and so on, as large as you can think of. And even larger if you can think of something larger than what you thought previously. So the motivation we're going to start with is looking at this function here. So x squared minus 1, x squared plus 1. And we're going to see what happens as x becomes large. The way we're going to do that is we're going to start with x values and we're going to plug them in. Actually, the book did it for us. I'll just show you the results. And you can follow along if you'd like. Basically, they tell us when x equals 0, plug that in. All right, remember we have like this f of x right here. X squared minus 1, x squared plus 1. And basically what they're doing is, if I zoom in just to let you know, so remember that f of x is x squared minus 1, x squared plus 1. So here they're doing 0 squared minus 1, 0 squared plus 1. So that's minus 1 over 1, which is minus 1, right? And they keep doing that with positive 1. The real interesting thing happens when you go further down to large values. So basically when you go, x squared minus 1, x squared plus 1, we have 1, 0, 0, 0, 0. Should replace that 0 with a minus 1, so it's going to be, so 100 squared is 1, 0, 0, 0, 0. Right? So 10,000. When you take 1 out, you get 9. Bunch of 9s, right? 9,999. And here you get 1, 0, 0, 0, 1. When you do the division, you get this approximately. And that's when things start getting interesting, because the larger the x value you get, the closer to 1 it looks like your result is getting, right? And that's the key idea here. You're trying to make x as large as possible, and then you're trying to know what happens to the f of x, right? This is not a very good estimate at all, the first one, but the last one, you can see that the numbers are stabilizing. They're getting closer and closer to 1. There's not going to be a huge change anymore after this, right? So we would guess that the limit of f of x as x goes to plus infinity, and that's the notation, right? X goes to plus infinity or approaches plus infinity is 1. Okay, take a look at this, try and understand what I said. Going back to the table is necessary, and try and understand what this equation here means. Okay, and just read this first paragraph here on this slide, because it does explain a little bit of what I just said. As x grows larger and larger, you can see that the values get closer and closer to 1. In fact, it seems that we can make values of f of x as close as we want to 1 by taking x sufficiently large. Okay, which goes back to when we say as close as we want by taking x sufficiently large, we're hinting towards that formal definition, right, of limit. We're going to talk about this a little bit now. So this is the notation. And intuitively speaking, we're talking about a function that's defined after some value, and we say interval a to plus infinity because we have to be able to plug in large values. So that's just a technicality. And we just mean exactly what we just said, right? We can make f of x as close to L as we'd like, as long as we make x large enough. Okay, f of x can get as close as L as we'd like, if x is large enough. So here's a couple of graphs exemplifying it doesn't have to work just like it worked in the previous example. Here, for example, we saw x getting larger and larger, approaching 1, which is what we saw in the previous example. That could be the case, but it could be that it's getting smaller and smaller and approaching L, right? Or it could be like oscillating around L as long as it's getting closer and closer and closer and closer all the time. What it's not allowed to do is to get closer and closer and then leave and never come back. That's not allowed to happen. As long as it gets closer within a certain strip around L and doesn't leave that distance, then we can say that the limit is L as x goes to infinity or goes to plus infinity. Okay. Now, what does that have to do with horizontal asymptotes, right? That's exactly what we have in those three examples. This red line, y equals L, is a line that the graph approaches as x becomes larger. So that's what we call a horizontal asymptote, okay? And they say here going to the far right of the graph, but if we go to the far left, we may also encounter horizontal asymptotes. And you can see that right there. If you go back to the example that we started with, because both numerator and denominator include x squared, if you plug in stuff instead of x equals 100 and plug in x equals minus 100, you also get similar results because x squared, right, eliminates the negative sign of x. So we also have something to the left, okay? And you can note here that we add a negative sign to our limit. X approaches minus infinity, or goes to minus infinity. Approaches minus infinity is not something we say a lot because minus infinity is not a number, and it doesn't matter how large your number is, it's very far from infinity, right? We can just say as x goes to minus infinity or x goes to plus infinity. Okay. And intuitively means the same thing, right? X approaches, or rather f of x can be made close to L by requiring to be sufficiently large negative. Something that confuses people sometimes is we say large negative rather than saying very small. In general, when I say small, I'll mean close to 0. Definition 2, again, is showing us that what happens to the right side doesn't matter for us now. Now we're looking at what happens on the left side because we're saying x approaches minus infinity. But we want the same type of behavior that we wanted for the other example. Okay? As long as it's to the left side now. And there you go. And there's the definition. We say that y equals L is a horizontal asymptote if one of these two things happens, either the limit as x goes to infinity of f of x equals L, or the limit of x goes to minus infinity of f of x equals L. So that means we can have possibly two horizontal asymptotes in a graph. One on the right, one on the left. We can have none if none of the two limits exist. So we can have no horizontal asymptotes. Or we can have one in case both limits are the same. So let's take a look at examples. Find the limit of 1 over x as x goes to plus infinity. So right now we can use different techniques, but what I'll say first, I'll tell you to notice, right, that, so let's investigate this. Notice intuitively what's expected. Just look at what was given to us. X is getting larger and larger, so 100, 1,000, a million, a billion, a trillion, and we're dividing 1 by x. So that means 1 divided by 100 by 1,000, that's getting smaller and smaller. Okay? So let me investigate this by using a table. So let's say x, f of x equals 1 over x. And I'll use my calculator too, so you can pull yours out as well. So let's start. I'm not going to do like x equals 1, 2, because what I'm interested in is what happens when x gets larger and larger. So we'll start with like 100 because I think it's a large number that's small. It's a good starting point. So 1 over 100 is 0.01. Okay, so if x equals 1,000, then 1 over 1,000 is 0.001. And if I add another 0, then 1 over 10,000. That's just taking another 0, moving the decimal point once to the left. So as you can notice, one can see that as x becomes larger, f of x becomes closer to 0. And I'll use the word smaller to refer to that without, risk of confusion. So it is fair to say that it's actually a fair guess to say that that's what happens. Okay? I'll let you work the details of the other one on your own, but the same should be verified. The only difference that we have is x is becoming very negative, very large negative, so minus 100, minus 1,000, minus 10,000, and so on. So all you're going to see is negative signs in front of those numbers that we just, in front of those numbers here, right? Negative signs, you're going to see them there. But that doesn't change the fact that they're close to 0. They're just to the left of 0. But I'll let you work on this second example on your own. You can see what we're told here, right, as the answer. You can see what happens when we graph these. So if you graph the function y equals 1 over x, so this guy here, then that's the graph. And as you walk down the graph towards the right side, you get closer and closer to the x-axis, which is like red or, I don't know, pinkish in the graph, to show you that this is what's going on. Okay, same thing if you walk down the left. Okay, so we do have horizontal asymptotes. Okay, so it's expected. So this is a theorem so that we don't have to keep plugging stuff down a table or into a table, or keep using the definition of limit. You can prove this using the definition of limit. If you're interested in math, theoretically, you can practice writing a proof for this. But this is something that we're going to use without justification from this point. Whenever you have something like this, some polynomial, right, x to the r power, as long as r is positive, then 1 over x to the r, the limit of it, as x goes to plus infinity, then that's 0. Because intuitively, right, like we said before, intuitively, as x gets larger, because r is positive, x to the rth power gets larger and larger as well. 1 divided by something very large gets very small, close to 0. Okay, so that's something we're going to use right now, and from now on without justification, because we've already done it. Okay, but how do we handle something like this, right? How do we handle a limit that is not in that basic form that we just saw? Here's what you're going to look at. You're going to look at the denominators here, at this guy and at this guy, and numerator and the denominator, and you're going to look at the highest powers of each. So at the top you have x squared, which is the highest power, and at the bottom you have x squared, which is also the highest power, and they are equal. If they were different, you have different ways to go from there. I like to choose the highest power of the two, but because they're equal, all you do is you divide by. So you're going to go 3x squared. You divide by that number, right? So let's go with the example. So I'll divide this by x squared, and I'll divide this by x squared as well. Remember that dividing is the same as writing it as a fraction like this. So you have here's how it works. I have to add a couple of pages to make it work, but here's how it works. We have 3, and I do it slowly just this one time. Right, I can put 1x squared underneath each of those terms. And now you simplify this. We've done something similar in Math 141 if you took it. So what you do now is you look at what happens when you cancel these two out. You get a 3 on the top, and then at the bottom you get 1 over x, and then here minus 2 over x squared, and then you get a 5 here by canceling these two out, and then 4 over x, and then a 1 over x squared. So that's what you want to cause, that's what you want to make happen. If for some reason the two exponents, like I said before, it's not x squared and x squared, it's like x cubed or x squared, you can either choose the smaller of the two, like divide both by x squared, or choose the larger of the two, divide both by x cubed. It's your choice. I prefer the larger one. It works better this way, but the most important thing is that you reach a point that's similar to this, where all you have are numbers, or 1 over 2 over x squared, or x cubed, whatever, so that you can use that theorem to note that this is 3 minus 0 over 5 plus 0 plus 0. Because what's happening is you have, for example here, right, 4 divided by x is getting larger and larger. So it's like 4 divided by 1,000,000. That's very, very small. Doesn't make a difference, right? So basically the denominator gets closer and closer to 5. So that's 3/5. So that's the trick that we're going to use most of the time when we have limits at infinity. Look back at this and make sure that you understand what I just did. Okay, here's another example. I'll do this one a bit quicker, but this time you have to be more careful. Look at the highest power at the denominator. That's a 3x. So the highest power here is x to the first power. The highest power at the top would be x squared, but because you're taking the root, that's just x again, right? So x squared, that's x if x is positive. So that's the most important thing to remember. Only if x is positive. Because if x is negative, then you're going to have to do something slightly different. So let's start with the most obvious thing, which is going to the right side. X goes to plus infinity while x is positive. So you're going to go 2x squared plus 1 divided by 3x plus 5 minus 5, excuse me. So I'll divide that by x, top and bottom. Dogs are making a little bit of noise there. So you're going to get something like 2x squared plus 1. So next page. Sorry. Always got to add, you always have to write the limit in whatever's underneath. Otherwise, maybe quicker if you don't, but otherwise your math is not correct. So what you have to be careful about, and that's what I'll change, is that you're going to bring this x into the square root, and to do that, you have to replace it by an x squared. Right? Because the square root of x squared is x when x is positive, and x is positive because I'm making it very, very large. Now here I can do what I did before, and then finally, or almost finally, you can cancel things out like we did in the previous example to get 2 plus 1 over x squared divided by 3 minus 5 to the xth. And then using that theorem, right, as x gets larger, this is close to 0, this is close to 0, so this is square root of 3, or 2 over 3. So I did it slightly faster than before. But now what happens when we do the other example? What happens, right? It's the most important thing there. So let's look at the other, because we're looking for horizontal asymptotes first. So we started by looking at the limit of f of x when x goes to plus infinity. Now I have to look at the limit of f of x when f goes to minus infinity, because that's going to be an asymptote to the left. So let's go ahead and add another page so that we can work on this. And I'll use different colors so that you know. So I'll go the limit x goes to minus infinity. So x is very large now, but it's negative. So like minus 1,000, a billion, a trillion, whatever. So that will be the limit. X goes to minus infinity. Square root 2 x squared. I forgot. Plus 1. 3x minus 5. So I divide by x again. However, right, I don't have any issues yet, but when I try and do what I did before, which is to bring x into the square root, I have to be careful. You can start thinking about what's going to happen while I write. So the bottoms is the same, so I got 3 minus 5 over x. It's not going to cause any trouble to me. But now, square root of x squared, I can't just write x squared and bring it into the... I'll do something similar. I'll do this, but it's not true that the square root of x squared is just x. That is not true. This is something that, if you haven't thought about it for a second, it does confuse you. But the answer for this is going to be minus x, and that's because x is negative. We're making x very, very, very negative, right? And that's the reason. You can plug in a couple of examples. Say x is minus 3, right? X squared is positive 9. Is it true that the square root of 9 equals minus 3? No, right? Square root of x squared is not x, because x is negative. It's not true. You have to change the sign by adding this artificial sign outside. So because x is negative, you add a minus sign here. And that's only because we have x squared. If it were x cubed, would not have an issue. If it were cube root of x, would not have that issue. So we continue. So now it's the limit. X goes to minus infinity of minus the square root. So the same thing happens now. Plus 1 over x squared. 3 minus 5 over x. So that's minus square root of 2 over 3, because this goes to 0, this goes to 0. That's the answer. So we now have 2 horizontal asymptotes. Okay? That's what's going on there. So the vertical asymptotes are going to happen when... Let me add a page just so I can write my conclusion. So y equal to square root of 2 over 3 and y equal to minus square root of 2 over 3 are horizontal asymptotes. Are the horizontal asymptotes, because there can't be any more. Okay, now for the vertical ones, if you go back, in black this time to sort of mark the change. have to look at the denominator. So 3x minus 5, you make it equal 0. 3x equals 5, right? X equals 5/3, and that's a possible location for my vertical asymptote. And to confirm it, you look at the limit as x approaches 5/3 of 2x squared plus 1 square root over 3x minus 5. And in fact, this is going to be, so you have to look at two different limits. You have to look at the limit from the right and at the limit from the left. So add another page here. So you have to look at these two. If one of them is either plus infinity or minus infinity, meaning the value of f of x gets larger and larger, either positive or negative, as x gets closer and closer to 5/3, then this is a vertical asymptote. So this limit is just to confirm. So I'm questioning, is this true? Is it true that this is plus or minus infinity? It is true, in fact. I'll let you work on the details to see. But the main point is that the top, as you plug in 5/3, so this here is just any number, 2 times 5/3 plus 1, the square root of it, just a number. It's non-zero, and the bottom is 0. So basically what you're seeing is this here, and right here, so you see this is just an observation. This is some number that's not 0 divided by 0, right, basically. And I use quotation marks so you see that I don't really mean divided by 0, so the bottom's getting closer and closer to 0. So it's expected that the result's going to get larger and larger. The only situation in which you would have to test the vertical asymptotes more carefully is when the top also approaches 0, and then you'd have to cancel things out to see if actually that's a vertical asymptote or a hole or a jump type discontinuity. Okay? But okay. I'll let you work on the details of this on your own and convince yourself that that's true, but that's the answer. Let's keep going. And we're sort of segueing into infinite limits at infinity. So two different things that I mentioned at the beginning. At infinity means x is getting larger and larger. Infinite means f of x is getting larger and larger as well. So here's an example, and here's the notation. X is going to plus infinity. Sometimes you don't write the plus, you just write the infinity, which is what they're doing here. Sometimes you're going to do minus infinity, minus positive infinity, minus infinity. So all of these four possibilities are the study point of this part, or our main objective to study in this part of the slideshow. Now we're going to see what's going to happen. This is easy to see if you plug in same again, table study of this first example. If you plug in something like 100, 100 cubed is, you just triple the number of zeros, so it's getting very, very large. Plug in 1,000, you triple the number of zeros, so you have 9 zeros now, right? Okay. So as x gets larger, f of x is getting larger and larger as well. Okay. So that's to say the limit x goes to infinity, x cubed is infinity. And if I don't write a plus sign, then that means it's plus infinity. Okay? Same's going to happen, or something similar is going to happen with this one, except that we're now going to have a negative sign. So I'll let you work the details again, but you're going to see that the limit x goes to minus infinity of x cubed is minus infinity as well. Just plug in some numbers on the table and you're going to see. Because you're multiplying x by itself 3 times, you get a negative sign, okay, as an output. Precise definitions are due, so this is the idea. Basically, you're saying that for every epsilon you choose, so you want to make f of x close to L. Close to L means within epsilon distance, right? Within an epsilon distance of L, or epsilon close. And you can do that as long as you choose an n so that x is larger than n. Okay, it's similar definition as before. Okay, let you read this on your own. If you need to clarify, I'm not gonna work on this too much. And same idea as before, right? You have a strip of length epsilon. As x gets larger, f of x enters that strip and it doesn't leave it again. Okay, so you have like x L minus epsilon, L plus epsilon like you had before, but rather than getting closer on a horizontal strip as well, a vertical strip like this, right? Which is what we were working on before. Now it enters that strip as we go to the right and it doesn't leave. Okay. Same thing happens when you go to the left if you wanted to look at that. Okay, there you go. Similar for when x goes to minus infinity. You want to make f of x epsilon close to L within an epsilon distance of L. And you do that by making x less than some n. That's to be determined depending on what epsilon you chose. Okay? So now let's look at this. Let's use the definition to prove this. So we're going to prove that this limit, rather than just using intuition, we're going to prove using the definition. So let epsilon be any positive number. And I'll use like a little draft, a different color so that you see. So this is my draft. I'm trying to make 1 over x within an epsilon distance of 0, right? That's what I want to do. Okay, so that means to say 1 over x in absolute value is less than epsilon. 1 over absolute value x is less than epsilon. I move absolute value over and I move epsilon over. Okay, so that's what I have. And I'm looking at x going to plus infinity, right? Positive. So the absolute value of x is x. So because x is positive, and that's true because x is going to plus infinity, so it's getting larger and larger with a positive sign, absolute value x equals x. So that means to say that 1 over x has got to be less than, sorry, 1 over epsilon, excuse me, less than x, right? So that's my n. And now I just write my proof. So I'll say choose n to be 1 over epsilon if x is greater than n, then x is greater than 1 over epsilon. So I'll do my math here backwards. I start here at the bottom now and I walk back. You know, basically, I'll do it in purple like this. I'll go backwards. I'll go here, here, here. Use my draft now. So I'll say. I guess I don't have to do that. I can say this too, right? I can say f of x minus 0, the absolute value, that equals to 1 over x minus 0, 1 over x. So because 1 over x, if you look at this, right, x is greater than n, 1 over x has to be less than 1 over n. because you're taking the opposite, right? Just think about true numbers. Because 1 is less than 10, for example, 1 over n is more than 1 over 10. Because you're dividing by something smaller, you're getting a larger result. So what I'm saying is, because x is larger than n, then this is, so just to continue, first this is 1 over x, because x is positive. And then this is less than 1 over n, which is 1 over epsilon, which is epsilon, as desired. And then I'll just write like a conclusion. And sometimes people write that little like a square filled in to indicate that they finished their proof. Some people like a QED at the end. And that's it. That's how you prove this. You choose an epsilon. You're saying basically, for any epsilon that you give me, I can give you an n that makes things work. Okay? And then we're good. This is draft. You don't have to include this part in red in your computations. You just write it down and you figure it out. And here's, again, like I guess a visual representation of what's going on, right? Of what happens when you're having infinite limits at infinity. So you want f of x to go beyond that horizontal green line, and you do that by making x go to the right of the sort of orangish yellow line of n there. So that's what's going on. And they're going to give you a precise definition. I guess it's a good idea just to read this to understand what's going on, but I'm not going to ask you about this too much. The idea is, for every positive number m that you choose, there's a corresponding positive number n, such that when x is bigger than n, you can make f of x greater than m. Okay? And you can make similar definitions for the other ones. I'll stop here. I'm not going to ask you to do too much of this, so I won't put too much emphasis on it. Thank you for watching that.